So it is my pleasure to introduce Dagmar on this fourth installation of the Neurosymbolic AI webinar series. Dagmar is currently an associate professor at the University of Vienna's Center for Translation Studies. Dagmar has a diverse background in computer science and linguistics and has been on the forefront of neurosymbolic AI for some time now. She has organized 6 or so semantic deep learning workshops across the semantic web and AI and computation linguistics venues. And more recently, she has explored how different usage, distribution, and other aspects of language impact neural systems, including large language models. Fittingly, her talk today is Understanding Natural Language with Neurosymbolic AI, and I'm very excited for this. So the plan is to hold questions until the Q&A, which will be right after the presentation, but you are welcome to post your questions in the Slack, in the Zoom chat, and I'll keep an eye on it there. Otherwise, the Neurosymbolic Slack has a channel specifically for the seminar series, and I'll post a link to that, and you can join and post questions, and I'll moderate from there as necessary. So with that, I'll give the virtual floor to Dagmar. Thank you.
Thank you very much for this very kind introduction. Can you see my screen okay and my slides? Okay, thank you very much. So I'm very happy for this invitation, very grateful for it, and also very happy to see a number of familiar people in the participant list. So today, what I would like to talk about is one of the main challenges of computational linguistics. Generally, there are those 2 or 3, depending on how you see it. So the one is natural language understanding, which is broadly defined as computational understanding of human language. And the other one is related to natural language generation. Sorry, I'm just trying to open the chat. Okay. Where the focus is really on producing coherent and meaningful, fluent language output. And usually this is really important for the interaction with humans. So typical examples are machine translation or dialogue assistant systems. And sometimes the speech recognition and processing is considered as a separate part because there are different technologies usually being used for speech recognition and processing. However, more and more these technologies come together to be able to process text and speech and even sign languages all together. So how can you see whether your approach to natural language understanding is any good? How can you test systems, evaluate systems? The most important thing to talk about in this area is this benchmark called General Language Understanding Evaluation, where a large number of tasks have been proposed and data sets in order to test different systems. So for instance, you have something like the corpus of linguistic acceptability or sentiment tree bank, research paraphrase corpus, and also the classical semantic textual similarity. Just to give an example for the COLA, where the focus is to determine if a sentence is grammatically correct or not. There are 2 sentences, and each participating approach needs to predict which of these is grammatically correct or not. Then another example is this research paraphrase corpus, where the idea is to determine if 2 sentences that are provided are paraphrases from one another or not. So here we have the example, the euro rose above $1.18, the highest price since its January 99 launch. And the second sentence is the euro rose above $1.18, the highest level since its launch in January 99. So it's quite clear that those 2 sentences are very similar and provide the same information. So they can be seen as paraphrases from each other. The follow-up on glue is a more challenging task, which is called super glue, where you have novel tasks to fulfill, to complete. and novel data sets. So for instance, you have the multi-sentence reading comprehension, which provides very short paragraphs and some multi-sentence questions that should be answerable from what is provided in this paragraph. Another task is the choice of plausible alternatives, which is you get a premise and two alternatives, and then you have to decide, or the system has to decide which one is more plausible. One that's more interesting for this context maybe is textual entailment. So you need to see whether the meaning of one text is entailed from the other text. And finally, inspired from the Vinograd Schema Challenge, which also focuses substantially on co-reference resolution, which means finding out whether a pronoun refers to one or the other noun in a sentence. And inspired from that, a group of researchers has proposed the Vino-gender schema, because gender bias is a substantial problem in large language models. And this data set can be used to test explicitly for gender bias in co-reference resolution. So they provide one sentence that has a person in it and an occupation. And the same sentence is then provided in 3 different versions, where each version has a different pronoun. This works well for English. For other languages, the non-binary pronoun system is a bit more complicated, such as for German, and not a lot of data sets exist on that. So I took inspiration from this fantastic publication of Hamilton and colleagues, and I'm extremely honored that the first author is here today, on how to define neurosymbolic approaches, because I find this very useful and very interesting. So first, Henry Kotz proposed 6 types in order to classify any kind of neurosymbolic approach. The first one is the symbolic neurosymbolic, which Hamilton and colleagues call sequential. This is really the most basic idea of using some kind of symbolic knowledge, which can really just be words, and transform that into vector space and encode the knowledge as feature embeddings or as embeddings of some kind of standard language model. The second one is already a bit more interesting, which is a nested approach. So symbolic neuro as nested architecture, where a reasoning system can be used in the primary as a primary system, and is then combined with neural components in order to arrive at some decision. The third type is called cooperative or symbolic. It's a situation where the neural network focuses on one task, such as, for instance, object detection, and then interacts via output or input with a symbolic reasoner specializing in some kind of task, for instance, typically question answering. Type 4 and 5 are now here presented as one, because Hamilton and colleagues classify this together as compiled, where Kotz sees 2 different types of systems. The one is where the knowledge is compiled into the network weights directly, and the other one is where the knowledge is compiled into the loss function. The last one, type 6, the neuro bracket symbolic, is kind of the holy grail, the ultimate goal. So it's an ultimate neural symbolic AI system or neurosymbolic system, which should be capable of completely integrating both ideas and be efficient at reasoning at the level of superintelligence or human intelligence. For this one, there are currently no approaches available. In the survey, there was no approach available. There keep on coming up new challenges on general artificial intelligence and really going beyond just predictions. So maybe who knows when this type 6 type of model might be available. The distribution of approaches per type is also taken from the same paper, where we can see that there's nothing for the last type 6. But then for the compiled, interestingly, there are already quite a few approaches. It's not very surprising that there are also quite a few approaches for sequential, since this was the earliest idea or earliest way of how to combine knowledge with neural networks. So one example of a type 4, maybe I would say, system, so compiled system, is one that tries to smoothly integrate the neural components with symbolic components, where the symbolic component mostly relates to symbolic rules and simple logical statements. The idea here is to provide this neurosymbolic processor, as the authors call it, Liu et al., in order to improve on the understanding and reasoning on numerical representations in natural language, since this sometimes still represents a very challenging task, especially in question answering. So all the green components here, including the initial encoding of text and information, are neural components, and then all the white ones in the middle take decisions on a symbolic level based on the output of the previous neural layer or neural component. And then in the end, hopefully, the output is able to predict which number is the correct answer to questions specific to numbers. So finally, to come to my take on neurosymbolic AI in combination with natural language understanding, today I will present 2 ideas. The first one is a variation on the type of knowledge. So this is not exactly a type 4 or 5 idea on neurosymbolic AI. It's more along the lines of the sequential. But what's interesting with it is that it's not general knowledge you would find in knowledge graphs easily, but more the idea of how you can encode metaphoric knowledge, or how well this has been already achieved in neural language models to represent metaphoric projections. And the second idea that I will present is one that has been tried for linguistic features, which is to linearly transform the internal representation of the language model in order to achieve a stronger representation of subspaces and analyze, so to say, vector subspaces that perform better on a specific linguistic feature. So Hewitt and Manning have proposed this probe for showing that large language models can encode or do encode entire syntax trees. So the type of trees that are represented when you parse natural language, and which show how individual elements of the sentence grammatically relate to each other. And the idea of what I will present today, which is joint work with one of our students here, is that this linear transformation can also be used to analyze the subspace of the vector space of the large language model that represents factual knowledge, and to see whether this idea strengthens the ability of the model to handle factual knowledge. So to come back to the first idea on a slightly different type of knowledge, the question with natural language understanding always is a little bit, how do humans actually understand natural language? So what kind of processes, experiences, what kind of knowledge do we use in order to understand what's being said or read or heard? One idea is that there are some kind of mental patterns and experiences that are being activated when we hear language, and that there's a lot of physical and spatial language understanding that is accompanied with those patterns of physical experience. This idea and this hypothesis is strongly inspired by embodied cognition, which is the idea that language is actually rooted in the experiences we make when we interact with our world and with others. And that these experiences are, when they are recurring, at some point formed into a schema that we keep on using in order to perform abstract cognitive processes and complex cognitive processes, including natural language understanding and reasoning. And one idea that has been proposed within this context is that of conceptual metaphors, where you perform a metaphorical transfer of knowledge structures from the physical to the abstract domain. So one example is, as a child, we have very early experiences of the basic concept of containment. Whenever we ourselves move into another object, such as a box, as a baby, for instance, or into a house, then these are already experiences of containment. Or when children learn that if you tip over a glass, the liquid that's contained spills out. So all of these different experiences of containment keep on repeating the notion of an inside and outside, a kind of boundary, and usually that there is some kind of boundary through which objects can move in and out into a container. This notion is also something that is believed and that we have been trying to prove for a while is a fundamental experience that shapes language. So we keep on using those ideas of physical patterns in abstract language. This can be observed in simple sentences such as, he's out of his mind, which is this idea of containment again. Or it is also very frequently used to express emotions, such as overflowing with joy, where the body is seen as a container and joy flows out of it. Also, if you say you've had a full life, the life acts as a kind of container. This type of metaphorical projection can be observed in general language a lot. So emotions, of course, is something where you find it very much. If you look at these expressions, I don't know where our relationship is heading, or we will go our separate ways now, then you might get the notion that this is about traveling, that this is about journey, paths. So in image schematic terms, this would be source, path, goal. And as a conceptual metaphor, these expressions describe the transfer of journey to the abstract domain of love, which is then the target domain. This can also be observed in domain-specific language, which is an interesting case. For instance, in finance, investments are frequently associated with containers. You invest your money in the stock market, where the stock market becomes the container for your money. Or something like conservatives in Congress gutted the National Endowment for the Arts. This gutted is an extremely strong case of containment, which really relates to intestines, and then the idea of taking away all the money from the National Endowment for the Arts and asking for private investment in this case. So both of these are examples of how physical ideas of containers are then represented to talk about money and investments in the abstract domain. So why analyze metaphor? Why do I talk about metaphors in this context of neurosymbolic AI? Because I think it's interesting to analyze the underlying conceptual grounding of this type of knowledge, which means the source domains and the target domains. And it's also because metaphoric language has been found to be extremely persuasive in social media when used by politicians, and much more so than if non-metaphoric language is being used. So this connection in communication to the very physical aspect of our experiences seems to resonate more with people. And I also believe that it is a challenge that's extremely interesting for computational approaches, because it's really knowledge that is very implicitly encoded in language and even very hard for humans to detect. So also for humans to agree on which source domain and which target domain are being represented. So I think it's a good playground to probe neurosymbolic approaches, and also to probe individual neural and symbolic approaches. What we tried was to see how well GPT 3.5 can perform this task of metaphor identification. So you give the model a sentence and you tell it which target domain this metaphor relates to. And then the model is supposed to predict the correct source domain. The important thing is that for this task, we did not provide any selection, any list to select from. So the idea is really to completely openly predict the source domain without giving the model any options of what the source domain could be, because I think this is the more challenging task. And then the question is how well this works. We also tried to integrate some knowledge to do few shot and fine tuning, where we show the model a number of target and source domain sets, such as here, our relationship is at crossroads, where the target domain is relationship and the source domain is journey. And then give it an open question, such as you're wasting my time, which hopefully is not true right now, where the target domain is time and the source domain is the one that the model should complete. Supposedly, having seen a number of examples should improve the type of domain and the type of prediction that the model makes. It should also probably be noted that it's important that the challenge is on the source domain, because this is the one that is more implicit. So the target domain can more easily be identified based on the words that are being used in the sentence. The source domain requires a lot more background knowledge and understanding of natural language to be predicted, because here you have the crossroads. So in this case, it's a bit easier, but for you're wasting my time, it's a bit harder to come up with the correct source domain from which this was taken. The results we did evaluate based on two similarity metrics, the one using knowledge graph embeddings that were trained on a combination of WordNet, Wiktionary, DBpedia, and WebAssembly LOD, which is called the library KGVec2Go. And we also tried with simple graph embeddings to see how well the automatic evaluation of those predictions work. We used a number of different data sets. So we compiled a version of an online repository by George Lakoff called the Metaphor List. This one performed best by far. Then we used the VU Amsterdam corpus to find a number of non-metaphoric examples, because it was very important for us to make sure that the model can also predict that there is no metaphoric projection whatsoever. And then we used the two languages of the LCC dataset, which are English and Spanish. This dataset is a lot more challenging because it has very long sentences, sometimes even paragraphs, in which the metaphor is to be found and annotated. And it's also domain specific. The metaphor list is a very simple data set with examples that researchers came up with. So it's not extracted from existing text, and it makes it a lot easier to understand and process this type of language. So very short sentences, very straightforward sentences. That's why the performance is a lot higher in the first one than in the other three data sets. What we also did was manually check for the domains and to see how well the knowledge graph similarity corresponds with our intuition on whether the domain can be acceptable for a metaphor. sometimes they're very close. So for instance, the model predicts nausea, and then the gold standard says it's a disease. So this is kind of close enough for us, for instance, to consider it correct. What's interesting is that the models were very easy to mislead with just some specific words. So to show an example, in the error typology that we proposed, words like a trough, which is associated with animals, immediately leads the model to propose animal as a source domain, which would then build the metaphor poverty is an animal, which for this case is not the correct prediction. This was something that we could observe a lot. So when there were any kind of even remotely related words to animal kingdoms or to animals, that it would really like to predict animals. There are also some errors that are harder to understand or explain from the sentence. Sally gave the idea to Sam led to a prediction of children, where we could only guess that GIF might have some kind of connection with children, and that's why. Some of the predictions are too literal, so I'm down to my bottom dollar is money is investment. There is not a lot of transfer, so this didn't work so well. Some examples should not be metaphoric, or some were predicted as not metaphoric, but they should be metaphoric. Sometimes the domain is, if you compare it to a knowledge tree, too far down in the hierarchy, so it's like too specific, or too far up, so it's too general to really present a good conceptual metaphor. And sometimes the predictions represented something that we call wrong sub-element. So wipe that smile off your face is the facial expression is a surface, where we said the facial expression is like the wrong sub-element of what could be predicted here. To come to the second idea, and the one that's probably more interesting, is this idea of how you can transform existing and already pre-trained vector spaces of large language models or pre-trained language models in order to target, in order to reinforce a specific subspace of this vector space that represents specific features. So one very interesting experiment is this experiment this proposal to do syntactic probing by Hewitt and Manning, which was then also taken up by Cogan and Rife and colleagues, where you use linear transformation and the squared L2 distance between two words, between two word vectors, in order to see whether the parse tree is encoded in the transformed vector space. And the distance between two elements in the parse tree are used in order to approximate the transformation matrix to the desired transformed vector space, to the desired idea of encoding this syntax tree. What you see on the right is a principal component analysis visualization of the context embeddings after they were transformed, where you can see that the embedding space really does assimilate or approximate this syntax tree idea. And our idea was to take this idea of transforming a vector space in order to analyze specific linguistic features, and then use it not to analyze linguistic features, but to test for the quality of factual knowledge in this vector space. To do that, we use a proportion of a very large existing data set for knowledge graph embedding, for knowledge graphs, the Wikidata 5M data set, and we use it in the form of embeddings. The idea is that if a knowledge graph is embedded, or the idea is that a knowledge graph is embedded if the contextual embeddings TS, so for subject, and TO for object, that were transformed by the transformation matrix B, then approximate the similarity scores of the knowledge graph embeddings of the original entities, the entity subject and entity object. To do this, we use the simple matrix of cosine similarity between the embeddings, and then train the matrix B with gradient descent in a supervised setting. And what you see here at the bottom is the loss function that takes the similarity, the cosine similarity score of the two entities initially, and the cosine similarity of the model predictions in order to have a regression objective, an regression training function here, and to approximate the similarity scores to those that are targeted, which are similarity scores between a pair of entities that is related by a specific relation. So for instance, the relation main subject of, or borders with, or familiar relations, family relations, basically. So this is the idea here. In order to test whether this idea has also worked and resulted in a vector space that more strongly represents factual knowledge, we use Pearson coefficient correlation, the Spearman's rank coefficient correlation, the mean squared error, and the root mean squared error, and a total of 2 language models, where BERT was used in 2 variations. So once the embedding space of the last 2 layers were used and then averaged over in order to obtain this embedding space, which is a common approach in also fine-tuning when you use those embedding spaces for downstream tasks or in a specific kind of evaluation setting. The same was done for GPT-2, since this is one of the GPT models that is publicly available where you can access the vector space directly. And then the second variation for the BERT model we used was to encode the entire information in the CLS token that's being used during training, and see whether the CLS token already contains enough information to improve on this, to really encode all of these, this factual knowledge. As you can see, the first table represents the results for the original vector space without any transformation. And the second table represents the results after the transformation, where a huge improvement in the coefficient correlations can be observed, and a huge reduction of the prediction error can be observed in the 2 error metrics. What we found was also that there are some relations that are particularly challenging for most of the models, which is geographic relations. So something like shares, border with, and also family relations, especially of historical figures, such as Elizabeth of Austria, spouse of Sigismund II Augustus. Nevertheless, I think these results already seem very promising, that something like a simple linear transformation using the existing knowledge graph, the existing knowledge in a knowledge graph, can really lead to further improvements for representation of factual knowledge in large language models. To also show a visual representation of the results, we used the T-distributed stochastic neighbor embedding visualization method, where you can see the embedding space before the transformation on the left, and then after the transformation on the right. And you can also see 2 example entities, which are the day after, which has a main subject relation to Cold War. And as you can see on the right, those 2 entities have not only moved to the bottom of the visualization, but have also moved closer to each other. I would really like to thank my two collaborators with whom I've been working on these topics. So Lennart Wachowiak is the person that I've been working on a lot for anything related to image schemas and conceptual metaphors. And Giacomo Munda from the University of Vienna and IBM is the mastermind behind this idea of transforming vector space in order to tickle out the subspace that represents factual knowledge. This idea, this second idea, is going to also be part of the interesting new book orchestrated by Pascal Hitzler and colleagues on neurosymbolic AI, and we are looking forward to submitting our chapter very soon. The idea with Lennart on probing conceptual metaphors has already been published in the ACL last year. So what are the next steps? What is still left to be done, so to say, for what I presented today? Well, the first thing that we are working on right now is to evaluate a very detailed, to design a very detailed evaluation setting for this idea of transforming a vector space, and to test how well the factual knowledge really performs in question answering, for instance, or in other downstream tasks such as natural language inference or textual entailment. Another step that I'm interested in particularly is to combine those two approaches and to really say, first we transform the vector space to reinforce the factual knowledge being represented or to unveil it, and then use this transformed vector space in order to predict the source domain of conceptual metaphors, and thereby test the accuracy in comparison to the original vector space, and to see whether this potentially, hopefully, would also improve the consistency of domain mapping, so that a model consistently predicts a specific type of domains and source domains. So before I will end this talk, I would just like to summarize with a short list of take-home messages. So first of all, I wanted to present this focus on a different type of knowledge, which is really from a cognitive theory called embodied cognition, and that this kind of cognitive grounding in natural language and in natural language understanding can provide quite novel and interesting challenges. There are also other types of cognitive information implicit in natural language, such as, for instance, pragmatics, where the meaning of the sentence entirely depends on the situation in which it is uttered, which is even more challenging because that would require to even consider the situation between speakers and to include this in the meaning analysis, so kind of situated cognition. I also hope that I could show that a linear transformation idea is very simple but effective method to represent vector subspaces in order to analyze some kind of specific features, as has been shown for syntactic features such as the syntax tree, and hopefully we could show that it can also work for factual knowledge. And as a conclusion, I would like to just point out a number of promises that any kind of neurosymbolic AI can and hopefully will hold for natural language understanding, related to this linear transformation idea or not. So the hope is that the reliability of factual knowledge becomes higher by integrating explicit knowledge and reasoning systems, and thereby the tendency of such models to hallucinate, which means to provide information or data that is not connected to the situation or request, or even wrong and misleading. The hope is also that it's possible that it becomes possible to learn from smaller data sets and with fewer model parameters. So for this transformation, the subset that we used of the entire Wikidata base 5M dataset was substantially smaller. I think it was so hopefully with innovative and simple methods that relate to neurosymbolic AI, we can reduce the need for huge data sets and huge model parameters in order to reduce the economic footprint of those models and the kind of storage and servers that have to be used to run them. One obvious promise or hope is also that it increases traceability and interpretability in any sense of those words, so that it's possible to understand why specific predictions were being made, why a sentence with one person giving something to someone else would lead the model to predict children. And finally, this kind of approach, this kind of research direction holds the promise that vector spaces can be directly adapted in order not to have to retrain very large language models and to lower the need for repeated and continuous experiments of fine-tuning, few-shot learning, and so on. And with this, I will end my talk, and I'm very happy to take any questions.
Awesome. Thank you so much for the excellent talk. That was quite a lot. So very awesome and a lot to take in. So we have about 10 minutes remaining that we can use for questions. And if you have questions, you can either post them into the chat and I'll try and take them in order for Dagmar. Otherwise, in the Slack, or you can raise your hand within the Zoom interface, and it should put everybody in order to have you ask questions yourself. Well, at least to fill some silence, I do have a quick question for you then, Dagmar. So earlier on, you were talking about how language and can be sort of thought of as a way of encoding physical experience. How do you think some of your work and this notion of like embodied AI and this connection between language and physical interaction, where do you see that going with that line?
I think it's a very interesting question. Thank you for that. I know that a number of people have been working on connecting a body to this idea of embodied AI, and to see how this entire notion can also be used to improve motion detection and robotics. So I think it's a very interesting way to use this kind of idea of image schemas and embodiment in also planning and schemas for robotics, which is kind of, I think, the direction that embodied AI might take, which is something that I'm also very interested in to participate in the future. Yeah.
Awesome. Thank you very much. Looks like Stefano.
Yep. Sorry, I was not able to raise my hand here on Zoom. I was not able to find the button, but thank you, Dagmar, for the excellent talk. Actually, I had a question, and the question is, since you have been talking about conceptual metaphors, for example, are you also working on some possible ways to disambiguate or to make emerge some latent knowledge related to conceptual metaphors? For example, if we take the crime is a disease metaphor, of course, we know how to map some elements of crime onto some elements of disease, but not all the disease are okay, like, I don't know, amnesia, to take one. And I don't know, are you already working on using large language models and then verify in some way the reliability of possible combinations and metaphors using the knowledge that is already there into language models, for example? Thank you.
Thank you very much. So if I understand you correctly, first of all, nice to see you again. It's been a while. And secondly, do I understand you correctly that you ask whether to use some kind of reasoning system to evaluate the output of the predictions of the models, and to see how similar these are to what we would presume to be some kind of gold standard?
Yes, but also to make emerge what is latent. So you will have generative models which are very good at producing conceptual, well, instantiations of conceptual metaphors, which are grounded in embodied cognition, of course. But the problem is that, for example, crime is a disease because it has some spreading nature, okay? And because it is affecting a patient, etc., etc. But there are diseases like amnesia, which are not spreading, okay? So there are, I mean, some diseases which are more prototypical than others, and this, of course, is related to the prototype theory, but this is totally another field. So I was asking if, are you already working on making emerge this part of knowledge and then be able to reason, of course, and not only in a neural way, but also in a symbolic way in some way? Thank you.
Thank you for this extremely interesting question. Since we've been working on something that's related to kind of logical representations on image schemas, I have not continued that line of work, I have to admit. So it's been mostly neural with a little bit of symbolic the last year or two. But I think it is very interesting to combine these two approaches and to really use explicit knowledge in whatever way to integrate it with this kind of idea of predicting source domains. Because as you say, there's a lot of latent knowledge that could strongly support the prediction accuracy if used directly in combination as a more advanced type of neurosymbolic approach. So not just type 1, but really go towards 4 or 5. And I think this is a very good idea. It would also be interesting to see how you could integrate this knowledge maybe directly into the vector space. So how could you bring this into the vector space and then use the reasoning system in order to evaluate how well the prediction improvement has been achieved, or how well the prediction was, how good the prediction was. So thank you very much. Good idea. Maybe let's talk.
Yeah, sure. Thank you.
Thank you.
All right. Do we have any more questions before the end of today's webinar? All right. I think it's safe to call it, and we'll free up a couple of minutes. Oh, you have one question from in the chat. Is a preprint available?
So for the metaphor idea, it's published. For the linear transformation, not yet. Not yet, but we are going to submit the chapter at the end of this week. So it's only a matter of time until it will come out. But you know, with books, it might take a bit. And we need to double check whether we can put it on preprint. If we can, I'm very happy to send a link. Thank you very much.
Awesome. Great. Well, thank you so much again, Dagmar, for your presentation today. And I think, Lauren, we can go ahead and close it.
Thank you very much for having me and for your interesting question and for the presentation.
All right. Thank you. Bye-bye.
Bye-bye.